We are now going to discuss Gaussian mixture models, the main topic in this lecture. And we'll discuss the shortcoming of Gaussians. So Gaussians are nice and simple and have closed form maximum likelihood parameters, but they are often not adequate for real-world data. And the reason for that is that real-world data has typically many clusters, and Gaussians essentially just represent one cluster or one blob of probability, and then a Gaussian fit will be poor. And the remedy is, if one Gaussian is not good enough, let's take many of them and combine them into a so-called Gaussian mixture model. And it will turn out that this Gaussian mixture model is a universal approximator, so it can approximate any density arbitrarily well, in principle. And then we'll discuss learning with the expectation maximization algorithm. So let's look at some data from the well-known iris data sets. And here we're just visualizing two features. And now the question is, how well will a Gaussian fit work here? And probably not too good, because this data has two very clearly visible two clusters. And if we fit now a Gaussian, so essentially the Gaussian will put the mean somewhere here, and the covariance will try to cover both of these clusters at the same time. And the problem here is that a Gaussian has only a single mode, and essentially it's just one blob of probability. And so the Gaussian fit will try to fit all the data with a single blob, essentially. And we will have some significant probability assigned in this region where essentially there is no data. And the problem is that we have actually two distinct blobs or clusters in this data set. So this should remind you of k-means. So a simple remedy or a simple attempt for a remedy would be, let's apply k-means first. So and we would cluster the data into these red dots and the blue dots. So recap, look back at the lecture notes for k-means if you need a refresher. But essentially we would cluster this data set into two clusters, and then we could just try to fit a Gaussian to each of these two clusters. And then we get a result as follows. So if we fit a Gaussian to this blue cluster, we would get like a Gaussian here. And it would, if we fit a Gaussian to the red cluster, we would get a Gaussian like here. And this already looks way more natural. So because we've pre-clustered the data and applied a Gaussian to, or learned a Gaussian for each of these clusters, and this looks very natural. But now we have essentially two Gaussians, so two models, but what we want to have is actually one density models. So how do we combine Gaussian components into one model? And the answer is that we consider a Gaussian mixture model. So what is that? So if we have if we have a random vector x, then a Gaussian mixture model consists of the following parameters or components. So we have uppercase k components, and this is symbolizing k-means. In k-means we had k clusters, and here we have k components. So Gaussian mixture models, they have high similarity to k-means clustering, as we will see later. So we have these k components, and so for each component we have a mixture weight, so W, and a mean vector, mu, and a covariance matrix, sigma. So we have in total, we have k mixture weights, and we have k mean vectors, and k covariance matrices. So mixture weights W1 to WK, mean vectors mu1 to mu-k, and covariances sigma 1 to sigma k. So each of these guys is a positive definite matrix. And yeah, so there must be, so the mixture weights must be non-negative here, and they must sum to 1. So this is a constraint we have here. Now let's just take all these parameters, so all the mixture weights, all the means, and all the covariances, and let's put that into a single set, boldface theta. So this just collects all the mixture weights, all the means, and all the covariances, and this is the collection of all the parameters of our Gaussian mixture model. And then, so a Gaussian mixture model is just given as a convex combination. And a convex combination is a linear combination where the weights fulfill essentially these constraints, so non-negative and sum to 1. So here this is the convex combination part, a linear combination with weights which are positive and sum to 1. So this is called a convex combination. And so the convex combination goes over densities. So here this here is the Gaussian density parameterized with the kth mean vector and the kth covariance. So for each k, this thing here is a Gaussian density, but a different one for each k, because each k can have a different mean and a different variance. So for each k, we have a Gaussian density here, and we just take a convex combination. So we just mix them with so a superposition, if you want, of densities, of Gaussian densities. And this gives you essentially a new density, the Gaussian mixture density. So yeah, again, so here this p, x, mu k, sigma k. So these guys here are Gaussian densities. And we just take a convex combination, so a linear superposition of these densities. And this is a so-called Gaussian mixture model. So some properties here. So you might ask yourself, is this like well defined? So yes. So this Gaussian mixture is always a proper defined density. So this is actually a two-liner to prove that. So a density needs to be positive and needs to integrate to 1 if you integrate over the whole state space. And if so, this always holds in Gaussian mixture model. So a Gaussian mixture model is always a well-defined density. And a useful property of Gaussian mixture models is that they are universal approximators of densities. So if you have a target density, a density you want to learn, and you're using a Gaussian mixture model, so in principle you can approximate any density arbitrarily well. So this does not hold for single Gaussians, because single Gaussians have only one blob of probability, and Gaussian mixture models can essentially approximate anything. And this is essentially pretty much related to what we discussed for single layer neural networks. So a single layer multi-layer perceptron, where we saw that these, even with a single layer, neural networks are universal approximators of functions. And so this here is pretty much the same story here. So we can approximate any desired density with a Gaussian mixture model. However, note that this is non-constructive. So in principle, we might need a lot of components. So our k, uppercase k, might be very large. And this is also not constructive, so we don't know how to find them. But it's reassuring that in principle, regardless of the density you want to model, you can in principle model this with a Gaussian mixture model if you have enough components and if you are clever enough to fit them. So how do we actually fit Gaussian mixture models? And the canonical learning algorithm is called expectation maximization, or EM. So this is the canonical learning algorithm for Gaussian mixture models, and in fact also many other models which we won't discuss here. So we'll only discuss EM in the context of Gaussian mixture models. And EM will ultimately look very much like k-means to you. So we'll discuss the steps of EM, and just to warm up, a refresher how k-means works, which Sibylle discussed the last time. So in k-means work as follows. So finding clusters in your center, what you do is you assign you initialize your cluster center somehow, and then you assign points to clusters by looking at the closest center. So each point is assigned to its closest center or centroid, and then you update the clusters by taking the mean of the assigned points, and then you repeat. And a pretty story will happen here in Gaussian mixture models, but it will be soft. So in k-means, this assignment of points to clusters was a hard assignment. You just assigned each point to the closest center, and then you updated the cluster centers. And here in EM, we will do a probabilistic or a soft assignment of points to Gaussian components. And so we won't do a hard assignment, but essentially each component could have generated a data point, and we will respect this and essentially do a soft assignment of data points to Gaussian components, and then essentially update the components via maximum likelihood using the assigned points. So a very similar pattern as in k-means, and we will see in a minute. We will see this more clearly in a minute. So in order to understand this, we'll need to interpret Gaussian mixture models as a latent variable model. So what does this mean? So look again at the Gaussian mixture density. So the Gaussian mixture density is just this convex combination. So this weighted sum over Gaussian densities. And now this mixture weights, as said, they are positive or at least non-negative and sum to 1. And so this looks like so these mixture weights themselves, they look like a probability distribution because it sums to 1 and it's positive. And essentially, if we want to interpret this mixture weights as probability distribution, this will be key to the EM algorithm. And in order to do this, so we will introduce for each data point xi, we will introduce a so-called latent random variable zi. So latent means it's not observed. So we observe the data, but we never observe this latent variable. But we figure that it exists, and this zi, so this latent variable, has a state space 1 to k. So k, again, is the number of components. And we will now interpret this mixture weights of the GMM as a prior distribution of this latent categorical variable zi. And the interpretation of this zi is essentially a component selector. So this zi essentially for each data point, it selects first a Gaussian component. And after it has selected the Gaussian component, we draw a sample from this Gaussian component, and this has generated xi. So this is essentially the generative model we attach to the Gaussian mixture model. So if we do this, we can all of a sudden interpret the Gaussian mixture model as a joint probability distribution over our data. And this artificially, if you want, introduced latent variables zi. So we include all these latent variables, so one latent variable per data point. So we have the data point and the latent variable, which essentially selects the component. So like zi selects some component, maybe k, for the data point. And this component then produces this data point by drawing from the corresponding Gaussian. And this is, so the joint distribution over x and z is just by the chain rule of probability is given by the prior over z times the conditional over the data given the z. And now this is the interpretation as the mixture weight, wk, and this is actually just the Gaussian component. So we see so that if we now would sum over all k, then we would retrieve our Gaussian mixture. So if we sum out the latent variable, we retrieve our Gaussian mixture. So because the prior over z is just this wk, and the component is essentially just the conditional distribution over the data given this latent variable. And if we sum out the latent variable, we exactly retrieve the Gaussian mixture model. So essentially we can interpret the Gaussian mixture model as a latent variable model, where we have this latent distribution selector which selects a Gaussian component for each data point. And now this gives us the entrance to the expectation maximization algorithm. And like in k-means, we have essentially a chicken and egg problem. And so we have two problems, both of which would be simple if we already have solved the other problem, and we will essentially iterate this. So very much like in k-means. So the first problem is given our latent variable model, so like with the component selector and our data, so what is the probability that a data point belongs to a certain component k? And this question would be actually easy to answer if we already had the true parameters. But note, we are actually currently learning the parameters, so we don't know the true parameters. But if we assume for a moment that we would already know the parameters, then this answer would be easy. Just compute the posterior over the set, so like the component selector using Bayes' rule. So the probability that we have selected the kth component given the data is actually just proportional to the prior over the latent variable times the conditional over data given the latent variable z. So this is just Bayes' rule. So like the posterior over z given x is just the probability of x given z times the prior of z. So this is just Bayes' rule. So here we are missing the normalizer. So therefore this is proportional here. So again, p of z given x is just p of x given z times p of z. and then we actually would have a normalizer here. So this is just proportional. And we just define this as alpha ik. So this here is just the Gaussian density for the kth component. And this is just the mixture weight for the kth component. And we just define this term as alpha ik. So I is the sample and k is the component number. And if we normalize this now, so here we normalize these alphas, so we divide by the sum of the alphas, we get exactly the posterior of the component selector given data. So this is just normalizing the alphas gives us the posterior of the component selector given data. And we define this as gamma ik. And this gamma ik can now be seen as responsibility. So this is the probability. If we see the data point and we have the true parameters, this is the probability that this data point stems from component k. And it's now very similar as in k-means. And essentially in k-means, we also implicitly had these gamma ik's, but they were binary and a hard assignment. So essentially each data point I, so the ith data point, was assigned exactly to one component. Therefore, like there was one k prime, where gamma ik was exactly 1 and all the gamma ik's, the other would be 0 for all k's not equal k prime. So in k-means, essentially this assignment was hard and a binary vector, and here we essentially have a soft assignment. So here we are not completely sure which component has generated our data point, and we essentially just represent this with the posterior, given the data point, which component has actually generated this data point. And this is, the answer is this gamma ik's. Yeah, so gamma ik's is a soft assignment, so it sums up to 1. So in k-means it was binary and hard, and now here in expectation maximization it's soft. But otherwise it's pretty much the same as in k-means. So great, so this is the first problem. Which component has actually generated my ith data point? And the answer is essentially this gamma ik's. These are the responsibilities. And the key was that we already know the parameters, but we don't. And this gives us essentially the second problem. So if we had, so this is the second part of the chicken and egg problem. So what are the maximum likelihood parameters theta? And this would be easy if we already would know the true soft cluster assignment gamma ik's. Because then we actually could just do maximum likelihood by essentially just doing a weighted maximum likelihood variant. So this is pretty much as the maximum likelihood parameters for the Gaussians, so which we discussed in the last section. So these are, if we just fit one Gaussian, are the maximum likelihood estimates. And if we do now just a weighted version of this by incorporating our weights gamma ik, so each data point is weighted with gamma ik, and we normalize by the sum of the gamma ik's, summing over all samples. This essentially is a weighted mean, and similarly we have a weighted covariance. And we also have the WK, so the mixture proportions. They're essentially just the expected frequency that latent variable, so that all the latent variables assume a certain state. So this is just how often is how often is actually a latent variable selecting the kth component. So all of these parameters here is essentially just weighted updates, so weighted maximum likelihood estimates of our parameters, so a weighted maximum likelihood estimate. And this assumes that we have already this gamma ik's. And essentially this is pretty much the same story as in k-means. So in k-means we just, the assignment was hard, so these gamma ik's were hard. And we would update the mean vectors with essentially exactly the same formula. So this is, if the gamma ik's were hard, like in k-means, this is exactly the same as you would do in k-means, but now we have just a soft assignment. And so the other difference to k-means is that we also have the covariances here, and that we also have the weights here. And now essentially these are the two problems, the chicken and egg problems. So like, which component has actually produced my data? And the answer, if the parameters were given, the answer would be gamma ik. And if the gamma ik, so the cluster assignments were given, what are the maximum likelihood parameters, then this would be the answer. Now the story of EM is that we just iterate these two problems. So here's the expectation maximization algorithm, so iterating chicken and egg problem. So we have data and we have a number of components, and the output will be our GMM parameters. And so the first step is that we just initialize the parameters somehow, either randomly, or we could first apply k-means and then get initial estimates for all of our parameters. And then we have essentially two steps, the E step. And the E step is essentially the first part of the chicken and egg problem. So we had this alpha IKs, which essentially are just so I is the sample index, K is the component index. So we just take the current weight for each component and multiply it with the kth Gaussian density evaluated for the ith sample. So IK, K runs over components, I runs over samples. And by normalizing this alpha IK, so by just dividing it by the sum, we get essentially these gamma IKs, which are on the posterior, the posterior of the component indicator given the data. So this is like a soft assignment of data points to components. And so using this gamma IKs, we essentially just do a weighted maximum likelihood estimation step. So we get new mean vectors by just taking a weighted mean, and we get new covariances by taking a weighted covariance, and we get this the cluster proportions by essentially just summing over the soft weights and normalizing by n. And we essentially just iterate these two steps until we run out of iterations or until we are converged in likelihood. So a bit more complicated than k-means, but essentially very much the same story, a chicken and egg problem just iterated. So some nice properties of the EM algorithm is that it's monotonous in log likelihood. So EM guarantees you that in each iteration, the log likelihood of the GMM, of the Gaussian mixture model is guaranteed to increase or stay the same. And then essentially you have proof that you are already converged. Therefore, you can actually monitor the log likelihood, and if the log likelihood does not improve enough, then we can actually also stop. A problem is that the log likelihood is non-concave, so in the parameters, and therefore we can only guarantee that we achieve a local maximum with expectation maximization. And also a property of EM is that in the beginning it increases rapidly the log likelihood, and later it has a rather slow convergence. So if you're already close to the optimum, it converges slow, but in the beginning it really jumps up in terms of log likelihood. So let's give an example. So let's fit a Gaussian mixture model with two components to the iris data, and we initialize the cluster proportions or the component proportions with 0.5. We just initialize the mean vectors uniformly at random over the data range, and the covariance is initialized as diagonal with 1, so as the I matrix. So here, this is again the iris data, and here I've clustered it again with k-means, but this is not used by EM. So just to visualize better, so like we had like these two clusters given by k-means, and here this is the initialization. So the first component gets somewhere initialized up here, and it has this unit covariance matrix, and therefore we have these circles as contour lines. The other component is initialized somewhere down here, and this is actually the density of the mixture model. So, and after initialization, we have a log likelihood of minus 600 for nuts. So this is nuts is the typical unit. So it's like bits. So pieces of information, pieces of information. But here we take the natural logarithm, and this is commonly called nuts. So log likelihood is often measured in nuts. So minus 600. And after the first iteration, essentially the first component has jumped here, and the second component has jumped here, and we already reduced, or we have improved the likelihood to minus 300 nuts, and now also updated the mixture proportions. So this is after the first iteration. After 5 iterations, so first iteration is 300 minus 309. After 5 iterations, we are at 299, and yeah, this component has moved a bit. After iteration 10, yeah, the log likelihood has increased again, and this blue component, or the component belonging to this blue cluster, has moved closer. And after 15, so slowly the covariance starts to adapt to the shape of this cluster, and the likelihood has again improved. 20 iterations, this already looks pretty good. So like one component has nicely detected this red cluster, one component has nicely detected this blue cluster, and so this is the mixture model here. And essentially we already have converged. Like this is after 20 epochs, and after 25 epochs, essentially the likelihood hasn't really changed, and this looks actually pretty optimal. So like the two components have detected the two clusters in a nice way. So it seems that this is the optimal solution. So in general, we will only find a local optimum, but here essentially we were lucky and found apparently the global optimum. And this concludes the section on Gaussian mixture models. So we introduced Gaussian mixture models, which are convex combinations of Gaussian PDFs. And we said that they are universal approximators of densities. So you can, in principle, you can approximate any density arbitrarily well with a Gaussian mixture model. We introduced the EM algorithm, which is the canonical learning algorithm for Gaussian mixtures. EM has some nice properties. So it's monotonous. It guarantees to increase the log likelihood or keep it constant, so it can never decrease the log likelihood. However, so the log likelihood function of Gaussian mixtures is non-concave, so also EM can only guarantee a local optimum, and EM is highly related to the k-means algorithm, so by solving this chicken and egg problem, so assignment of data points to clusters or components, and then updating the cluster.